Okay, so in this problem, I've got a crate on a cart, and I want to find the smallest acceleration that will cause the crate to move on the cart. It gives me the static friction there. So let's go ahead and start by drawing a free body diagram of this guy. So my free body diagram will look like so. Okay, and of course I've got gravity acting right at the center. So that is going to be 50 times 9.8. Okay, then I'll have a normal force. But of course, now because of the motion and whatnot, right, this guy is going to be accelerating to the left as I pull it to the left. So the normal force will shift to the right like so. So I'll have my normal force here, which will be some distance x away from the center, like shown. I then also have a friction force acting in that direction, right? Because that friction force between the cart and the crate is actually what's causing that guy to move to the left, and that's what's causing motion. So I've got my friction force in that direction. Now I'll use my x and y equations like I typically do. So again, I'm going to have the acceleration in the negative x direction. Okay, so let me go ahead and set up my um, motion equations. I'll start by summing the forces in the x direction. And in the x direction, I have basically my normal force acting to the right, and that's going to be sine of 15. So n sine of 15. I'm going to have my friction force to the left, F cosine of 15. And what that's going to equal is my acceleration. And again, the acceleration will be to the left, so it'll be negative. I'll call that negative 50 times a. And that acceleration is what I'm actually trying to solve here. So now moving on to summing the forces in the y direction. In the y direction, I have n cosine 15. I have f sine 15. These are both pushing up. And then I have the weight pulling down equals 0. Now, I set up my x and y coordinates horizontal and vertical as opposed to at that 15-degree cutoff because of this very next point. What I have in the y direction now, the vertical direction, the acceleration is 0. You always want to set up your axes based on acceleration. We talked about that back when we talked about the kinematics, right? So you determine your axes based on how the object moves, and the object moves left to right, so you want to set up one of your axes left to right. Okay, so even though it makes n and f a little bit more complicated, having that 0 in acceleration is going to make my life a lot easier. Okay, so now I have to do the moment equation. Again, I have to sum the moment in this problem because I don't have any pure rotation. Okay, I have to sum the moments about g here. Okay, so when I sum my moments about g, I get x times n, that's going to be positive, and I get negative I'm sorry, I get negative 0.5 times the friction. Okay, again, the weight does not cause any moment because it's at g if I sum the moments about g. So again, I just have that normal force and then the friction force. Now this has to be 0 because again, I don't want, I'm basically finding the point right before it starts either slipping or tipping. Okay, so this is going to be 0 as well. So again, just like with y, I didn't have any vertical motion. I don't have any rotation here again because basically I'm trying to find, how fast can I move until it won't, tip or slip down the thing. Okay, so it only has that acceleration. So here are my equations of motion. Now, let's count up my unknowns here. I've got my normal force, got my friction force, got my acceleration, and I've got x, right? So I've got 4 unknowns, only 3 equations. Now here's where I have to start making assumptions. And again, the assumption is either that sucker is going to slip, okay, going down the cart, or it will tip over. And I want to figure out kind of which is the limiting factor here. So we'll start with slipping, okay? So for this guy to slip, what has to happen is my friction force has to equal its maximum friction force, which is 0.5 n. That's mu times n, right? Okay, so when that happens, okay, now I've got a new equation. I can use this, plug this guy into the sum of the forces in the y equation, and from that I can find that the normal force then becomes 447. Okay, once I know that normal force, okay, and the friction force, which again is 0.5 times that 447, I can plug both of those up into my x equation and find that my acceleration for it to slip is 2.01 meters per second squared. Okay, now that may or may not be the answer. I've got to figure out what acceleration caused tipping, and from that I can figure out which one actually occurs. Okay, now when tipping to occur, my x has to equal 0.3. Okay, so from that I can plug that into my moment equation, use that and the sum of the forces in the y equation, and I can find that then my normal force in this situation becomes 437. Okay, knowing that normal force, okay, I guess I also then learn that my friction force becomes, give me 1 second, 262. And again, that's basically using the bottom two equations, some of the moments about g and the sum of the forces in the y direction. Plugging both of those values into the top equation, I can then find that my acceleration for it to tip is 2.8 meters per second squared. Well, because of that, I know this is the answer because it starts slipping before it starts tipping. So at an acceleration of about 2 meters per second, this thing will start slipping down. So again, if I don't want this thing to move, I've got to keep it below 2.01 meters per second squared. So again, as with most friction problems, I've got to solve it a couple of different times to determine which case is actually occurring in a problem like this.